Okay, another theorem of three moments problem. In chapter 5, problem 130. It's the last problem in the chapters. It's 130M on page 313. It looks like this. There is a beam set up with three supports. So we'll have a reaction at A, a reaction at B, and a reaction at C. But there's a cantilevered portion of the beam with a 20 kilonewton load out 1.5 meters from the end, an 80 kilonewton load 2.4 meters from C. The length between B and C is 3 meters, so this little piece over here is 0.6 meters. I don't have space for all of it. I'm trying to fit it in. And then the other externally applied load is 60 kilonewtons just at the center of the other 3.0 meter segment. So each side is 1.5 meters between the externally applied load at A and B. Now let's start off with the theorem of three moments equation. I've got the wrong sheet. But this time, let's not bother with terms that don't exist. For example, go ahead and look at the equation, if you would, which is page 297, equation 5.9. The first term is moment at A times L1. Should we include that term or not? A is over here. Is there any moment in the beam at A? None. So let's not write it. Could there be a moment at B? Yes, that's the one we need to solve for. So let's write the next term. 2 moment at B, L1 plus L2. By the way, what are L1 and L2? Well, they're just 3 meters. They're always the distance between the reactions. In this case, again, they happen to be equal. They don't have to be. In this case, they are. How about at C? Is there any moment in the beam at C? Well, I think so. I bet I could calculate it too. I bet it's 30 kilonewton meters because 1.5 times 20, right, the 20 kilonewton force times the 1.5 meter moment arm will give me 30 kilonewton meters of moment or torque about C. So I know that there is a non-zero moment in the beam at C. So I better leave that term in. So let's write moment at C multiplied by L2. Now I think your author may have given us, yeah, I'm sorry, I've got to change my subscripts. Your author defined the points differently. He said that this is point A, point B is actually here where the 60 kilonewton load is applied. So this is point C, this is point D, and this is E, and then finally out at the end is F. So in the theorem of three moments, I can't use A, B, C. I have to use whatever goes with it. So for example, MB is actually just the moment in the middle. It would be above C. And MC is going to be the moment out here at point E. So I've got to generalize that theorem of three moments equation a little bit and change the subscripts. Everybody understand what I did there? It's the same thing, it's just the points are named differently, that's all. Okay, so that's the left-hand side. How about the right-hand side? Well, on the right-hand side, we don't have any distributed loads. In fact, all we have are some point loads. So what we have to do is include the effect of all the point loads. Well, notice that on the right-hand side, the only point loads to consider are point loads between the supports. We don't consider this one. It does not appear in the right-hand side of the equation. Its effect will appear, but it will appear through this term right here, the moment at point E. Okay? So let's just write the terms that we need for the right-hand side, and we don't need summations. So I will simply write P1, let's call this P1, this will end up being P2. So P1 multiplied by A1 divided by L1 multiplied by L1 squared minus A1 squared. And I'm out of space, so let me add below P2, B2 over L2, L2 squared minus B2 squared. I think that will work out. So what I'm talking about here is this load P2. Here's the distance B2, here's the distance A1. Make sense? Because remember, we have to measure from the support to the left, and for segment 1 from the support A to the right. Okay? And should I have negative? I've made a mistake. I need negative signs here. Forgot that from the equation. That's my fault. Notice something. We're assuming that loads acting downward will be plugged in positive. That's what that negative sign is for. If you had a load upward, what would you do? Well, you'd plug it in negative, and the two negatives would cancel. Okay? And this is just a line to note when my video ends. Not part of the equation. Well, in order to solve this, the unknown is going to be the moment in the center of the beam. In order to solve it, we better somehow calculate the moment at point E. So let me make a free body diagram that does not include this bit. In fact, basically what I'm suggesting is, let me separate it into two parts. So we'll pull off this segment and put the same effective loads on the right-hand side of this beam. So we've got a 20 kilonewton load and a 1.5 meter moment arm. Well, it's pretty easy to see that we have to apply a moment like this of 30 kilonewtons, right? Instead of being fancy and drawing positive direction moments, I'm going to be careful this time. So we have to do that. 30 kilonewton meters, 30 kilonewton meters of torque is required here to keep this in equilibrium, but also a shear of 20 kilonewtons would be required, because we have to have vertical equilibrium as well, not just moment equilibrium. What does that mean? Well, remember these, because we don't need them anymore. All I'm going to do is move these loads over to the beam. What that means is that we've got a 20 kilonewton shear, and let's see, equal and opposite would be this direction. So a 30 kilonewton meter moment. Notice what I've done here. All I've done is I have added the effect of that end segment. This is the exact same as if the end segment were still attached. And now I don't need to worry about it. I can forget about that end segment. It doesn't affect me anymore. Okay? All right. This will work out. So if we go ahead and rearrange and solve for the moment at point C, let's see, that would be negative P1A1 over L1 times L1 squared minus A1 squared, minus P2B2 over L2 squared minus B2 squared. I'd take this term to the other side, so minus ME L2. That's a 2, not a 1. And then divided by 2 times L1 plus L2. All I did was the algebra in one step. Now let me ask you a question. When I plug in P, am I going to plug in positive or negative? We're going to plug in positive. Right? Remember our discussion, we assumed that anything acting downward we plug in as positive. That's what that negative sign was for. So P1 and P2 will just be plugged in positive. A1, B1, L2, all L1, all these things will be positive numbers. How about ME? We have to be really careful here. Remember I said that there's a sign built into this equation, and that sign is that counterclockwise is positive. Turns out you can take the opposite sign convention. You've got to choose one or the other. Let's just take counterclockwise positive, because that's what you're used to. Okay? Counterclockwise is positive, but look at this moment. This moment's in the negative direction. So I have to plug in ME as a negative 30 kilonewton meter. Does that make sense? So I have to be really careful here. So let's plug in numbers and see what happens. Negative P1 A1 over L1. Well, P1 is 60. I'll check units separately. A1 is 1.5. L1, well, that's just 3 meters. Multiplied by L1 is 3 meters squared minus A1 is 1.5 meters squared. Let's check our units at this point. What do we have? Well, P, we know, has units of kilonewtons. A and L have the same units. They're both meters, so they'll go away. L and A, same units, meters squared. So we have kilonewtons meters squared for each of these terms. And that will work out well for this one, obviously. ME is kilonewton meters times meters would be kilonewton meters squared, so that works. divided by meters, we'll end up with a moment in kilonewton meters. So everything's okay. We don't have to worry about the units anymore. The second term, P2, is 80 kilonewtons. B2 is 2.4 meters. Notice that P2 is not centered in between the supports. So 2.4 meters is B2. L2 is 3 meters because it just so happens that the distance between C and E is 3 meters for segment 2. And so L2, 3 squared, B2, 2.4 squared. And then minus a negative 30 kilonewton meters. I apologize if this is all off the screen. All I'm doing is plugging in the negative 30 kilonewton meters for ME that I promised you. And I forgot I'm dropping units. Let's go to that. L2 is 3 meters, so that takes care of that term. And finally, 2 times L1 plus L2 is obviously 6, so let's just plug it in that way. So we can plug all of this into our calculators. When you do, or when I did, I came up with MC equal negative 26.6555. The 5's continue forever, as far as I can tell. And I just stopped it there, kilonewton meters. You can check this with your calculator if you want, but I'm pretty sure that that's correct. I've gone through it a couple times. Okay? Well, what's next? Well, the next thing to do is to, and I realize I'm sorry I'm out of time. Let me just finish this very quickly. And I think this will make sense. So the next thing to do is to simply take the left-hand segment, RA, remember I'm cutting it without the support. There's a 60 kilonewton load, and there's also the moment at C. So the moment at C, let's see. The moment at C, actually, we know that it's a negative moment, so it would be like this. Okay, so now I'll simply plug in 26.655 kilonewton meters. If you solve this for the reaction at A, what you find is that the reaction at A is 21.115 kilonewtons. Okay? And then if you do the same thing on the other side, so you take the other segment, 80 kilonewtons, and remember that we've still got our unknown shear load and our moment at E, which is known. Well, it ends up being in this direction, of course. We've got our moment at C. Let's see, let's draw it this way. So now it'll be the same moment here as it is here, in magnitude at least. You can find that the reaction at E is 37.115 kilonewtons. I'll let you guys go through this. All this should work out. Summing forces in the y direction for the entire body, you can find that the reaction in the middle, RC, is 101.77 kilonewtons. Okay, so this is all just statics. The last thing to do is draw the shear and moment diagrams. That's actually not too bad. The shear in kilonewtons starts off with the reaction at A, which is 21.115 kilonewtons. That goes over 1.5 meters to, let's see if this is A, then it'll go over to point B. At point B, there's a 60 kilonewton load, so that's going to take us down to negative 38.885, which we move over then another 1.5 meters, experience a load of RC, 101.77. That takes us all the way up, 62.885, but we only get to move along for 0.6 meters. Let's see, that's point C, before we are at point D. At point D, there's an 80 kilonewton load that takes us back below the axis down to negative 17.115. Okay, then we will move over the last 2.4 meters within well, to point E. And at point E, we know there's a reaction of 37.115. That takes us up to 20 kilonewtons. And if we continue out to point F, then we've got the 20 kilonewton load, which brings us back down to 0. What about the moment diagram? Well, the moment is just the integral of all this. And so if you integrate these areas, here's what you end up with. I'll just draw it for you. Moment in kilonewton meters. Gotta make it all match. The moment begins at 0, obviously, because there's nothing to the left of the beam. Add up this area. So let's mark off B, C, D, E, and F. Okay. This area comes out to a moment of 31.6725. We've got negative area, which brings us down to point C of negative 26.655, which, by the way, that was the moment we solved for. It works out. We've verified that it's correct. Adding up the positive area, it actually brings us up to 11.076. And at point E, we have to take all this negative area. That brings us back down to here, which is negative 30. And then, remember on point E, what was the magnitude of the moment? It was 30 kilonewton meters, right? Because of that externally applied load. And so that brings us back up to 0 at F, just outside of B. Okay, so this actually does work out well. Sorry I had to go so fast there at the end. Sorry I took so much of your time. But anyway, there's a shear moment diagram. And it's nice to know that it's all consistent. It all came out right. Okay. All right. See you guys next time.